At this point, I'd forgive you if you feel like the definition of the Laplace transform is a bit arbitrary, but it actually comes up in sort of a natural way when you think about Taylor series as a transformation. So for the following discussion, I am going to say a lot about Taylor series. So if you don't know what Taylor series are, I can only apologize because none of this will make any sense. But let's have a look at sort of an interesting way to describe what a Taylor series is doing. So if you have a function f of x, not every function is equal to its Taylor series, but for nice functions, they're equal to their Taylor series. So I'll write equals there here, even though we should be more careful than this. So the Taylor series is the sum from n equals 0 to infinity of f, the nth derivative of f, evaluated at the base point. And for now, I'm going to take our base point always to be 0, just to make things a little bit simpler, divided by n factorial times x minus your base point, but again, we're going to take the base point to be 0 to the nth power. All right, so one way to sort of think about what this Taylor series is doing is this coefficient here, we can think of this as a function. So let's call this function a of n. So a of n is the function nth derivative of f at 0 over n factorial. And so this series is really sum from n equals 0 to infinity of a of n times x to the n. Well, writing it this way, it's as if we started with a function a of n, and here n is the variable, and the possible values for n are 0, 1, 2, and so on, because those are the possible exponents in a power series. So we started with this function a sub n, and we put it into this transformation formula, which does a sum from 0 to infinity of a of n x to the n, right? And this formula tells us what our output is. And this output is a function not of the original variable n, but of a new variable x. And x is a continuous variable. So x can take a value in some continuous interval on the real number line. Not necessarily the whole real number line, but a continuous interval at any rate. So phrasing it this way, a Taylor series is just a way of starting with one function of n and transforming it into a new function, which is given by this formula. But the way this is set up, with our first function having just discrete input values like this, it kind of makes you wonder, is there some way that we could redo this, but with having a continuous variable for our input instead of a discrete variable? What would that look like? Well, I guess, first of all, we would want our function to be, n sort of implies that it's discrete, so let's pick a new variable name for our continuous input variable. T is a nice name, so our variable is going to be t, and t can be any real number, or at least any value in some continuous interval. So we're going to start with a function of t, and we'll do the same sort of thing. We'll have a of t times x to the t, but since t is continuous, we can't have a sum, right? There are uncountably many values for t in any real interval, and so if you tried to sum these things, it would never converge. Instead, what we need is an integral, right? The continuous version of a sum is an integral, so we'll do an integral from 0 to infinity dt. All right, so we get this sort of formula, but it's for anything involving integrals, it's really inconvenient to have your base be x. So instead of having a base x, you'd rather have a base e, because calculus is nice with base e. So we'll rewrite x as e to the natural log x. Okay, so when we put that into this formula, we get integral from 0 to infinity of a of t times e to the natural log x times t. So that's t times natural log x. Okay, now for this original integral to have any hope of converging, x had better be less than 1, right? Because we're raising x to larger and larger powers, right? Because t can go from 0 to infinity. And for this to have any hope of converging, x had better be less than 1. If x is bigger than 1 and you start raising it to really big powers, this is going to blow up. So we need x to be less than 1, but also we need x to be greater than 0, because if you let x be negative and you start raising it to irrational powers, you're going to have domain problems, right? Think about a negative number to a power of 1/2. You're going to start getting complex numbers, and things are going to get weird. And we're trying to stick to the real valued world, at least for now. So we'd like x to be greater than 0 just to make this thing defined. So less than 1 so that it converges and has some hope of converging, and greater than 0 so that it's defined. But if x is between 0 and 1, then that means the natural log of x, the negative of the natural log of x, is a number from 0 to infinity. So minus natural log x is a sensible value here. So let's call that s, just to give it a name. I've left off my dt here. So minus s is natural log x. But then we can rewrite this formula again. We get the integral from 0 to infinity of a of t times, a of t times e to the minus st dt. And look, this is exactly the definition for the Laplace transform of the function a. So the Laplace transform is kind of like a continuous version of a Taylor series. Thinking about it that way maybe doesn't give you much intuition for what it's doing, but it kind of hopefully gives you some idea of why this formula is where it is, and sort of the role that the Laplace transform plays. Just like the Taylor series sort of somehow turns a coefficient function into a full-blown function, the Laplace transform sort of transports you from one way of looking at a function to a different way of looking at a function.